Assalamualaikum warahmatullahi wabarakatuh. My name is Fateen Nuraribah binti AHMAD FADHLI, and today we are going to present two questions with different theorem. So now I will present the first theorem, which is integer modulo P has no proper non-trivial subgroups if P is a prime number. Okay, now I will prove for the previous theorem. So since integer modulo P is cyclic for subgroup generated by 1, all its subgroup must be cyclic. By the theorem of 6.14, for A that is not equal to 0 in integer modulo P, the order of subgroup element generated by A will be equal to P over the greatest common divisor by P and A, since the order of element integer modulo P is equal to P and A is equal to 1, where 1 is a generator of integer modulo P. However, the greatest common divisor by P and A is equal to 1 for all A in set of integer, since P is a prime. So for the orders of subgroup element generated by A will be equal to P for all A in integer modulo P. Thus, the subgroup generated by A must be all of integer modulo P for all A in integer modulo P. Hence, it is shown that integer modulo P has no proper non-trivial subgroups. Alright, so now I will show the example for the previous theorem. So the example is, show that a group G with at least 2 elements, but G has no proper non-trivial subgroups that must be infinite and prime number. So the solution is, first step is we let the order of element G must be greater than 2. If G has no proper non-trivial subgroups, then G and subgroup of element identity are the only subgroups. Next, we let A in G be a non-identity element. Then the subgroup generated by A cannot be subgroup of element identity. So the subgroup of element A is equal to G, hence G will be cyclic. After that, if order of element G is equal to infinity, then G is isomorphic with set of integer. But set of integer has non-trivial proper subgroup. Therefore, the order of element G will be proper subgroup of infinity. Then next step, we suppose that the order of element G is equal to n. Since G is cyclic, for every divisor of n, there exists a subgroup of H of order D. If D is not equal to n or D is not equal to 1, then H is a proper non-trivial subgroup of G. Therefore, the only divisor of n are n1, hence n is a prime.
Assalamualaikum and hi everyone. My name is NURUL Izzah ZAHRA and I am going to explain the second question. We choose the theorem number 5, which is the fundamental homomorphism theorem. So the next slide will show how to prove this theorem. So firstly, the theorem is if function phi is homomorphism from group G to group H, then the image of phi is isomorphic to G mod the kernel of phi. Now let's prove the fundamental homomorphism theorem. We will construct an explicit mapping from G mod the kernel of phi to the image of phi, and we will prove that it is an isomorphism. Then we let capital K denote the kernel of phi, and recall that the quotient group G mod K is just the set of left cosets A times K. Then we have wanted to find a map I from G mod K to the image of phi, so the input of this map is a coset of G of K to the phi of G. Next, we need to show the I is well defined. We must show that if AK equivalent to BK, then I of AK is also equivalent to I of BK. Suppose AK is equal to BK. We have AK is equal to BK, then multiply both sides with the inverse of B, and it becomes B inverse times A times K equal to K. It only can happen if and only if B inverse times A is element of K. By definition of the kernel, that means that phi applied to the element of B inverse times K has to be the identity in H. Then use the property of homomorphism to break it up as phi of B inverse times phi of A. From there, it means phi of A equal to phi of B. Hence, by definition of I of AK will be equal to phi of A. Then, the next step, we show I is a homomorphism. Show that I of AK times BK is equal to I of AK times I of BK. With some modifications, such as in the tables, we could show that I is homomorphism. After we show that I is homomorphism, we need to show that I is surjective or onto. This means showing that for any element in the codomain, which is in this case that is the image of phi, that some element in the domain, which is in this case is G mod K, that gets mapped to it by I. Next, pick any element in the codomain. Phi of A, element of image of phi. By definition, I of the coset AK is equal to phi of A, and hence I is surjective. So, the last step, we must show that I is injective or one-to-one. Show that I of AK is equal to I of BK implies A times K equal B times K. Suppose that I of AK is equal I of BK, then with some modification such as in the table, we could conclude that I of AK equal to I of BK implies AK equal to BK, then I is injective. In short, since I is a mapping from G mod K to the image of phi, that is a well-defined homomorphism that is injective or one-to-one and surjective or onto, then it is an isomorphism. Therefore, G mod K is isomorphic to the image of phi, and the fundamental of homomorphism theorem is proven. Next, let's see the example of fundamental homomorphism theorem. So from the slide, let's consider that the function f going from integer modulo 6 to integer modulo 3 given by this function in the matrix here. So 0 goes to 0, 1 goes to 1, 2 goes to 2, 3 goes to 0, 4 goes to 1, and 5 goes to 2. We can easily see that this is surjective homomorphism, and we also can see that the kernel of the things that map to the identity is going to consist of 0 and 3. This is equivalent to the subgroup generated by 3 in integer modulo 6. So now, using the fundamental homomorphism theorem, I could say that integer modulo 6 mod the subgroup generated by 3 is isomorphic to integer modulo 6. So, that's all from us. Thank you.